Okay, so we're going to move on to part 3, or part C in this case as it's written. We need to analyze the second derivative. I just wanted to remind ourselves what that original function was because it's written on the previous page. It's 2x squared minus 18 all over x squared minus 4. And what our derivative was, which was 20x all over x squared minus 4 quantity squared. So what does this allow us to do? This allows us to analyze the second derivative. Let's find that second derivative. How are we going to do that? Well, we're going to have to use the quotient rule, also the chain rule, but let's start with the quotient rule. So it says the bottom, which is x squared minus 4 quantity squared, times the derivative of the top. Well, the derivative of 20x would be 20, minus the top, which is 20x, times the derivative of the bottom. We'd have to use the chain rule, drop the 2, keep the inside just the same, so that's the x squared minus 4 to the first power, times the derivative of the inside. Well, the derivative of x squared minus 4 is 2x. All of this is over x squared minus 4 squared squared. So let's do some more simplification here. Looks like I have 20 times x squared minus 4 squared. And then I have a minus, and then I have a 20x times a 2 times a 2x. 20x times a 2 times a 2x. So that would be what? 20 times 2 is 40 times 2 is 80x squared times x squared minus 4. And this is all over, well, x squared minus 4 squared squared would be x squared minus 4 to the 4th power. Okay, so we need to do some work there. Notice in the numerator we can factor out an x squared minus 4. So if I factor out an x squared minus 4 on top, the first term I'd still have a 20, and I'd have one of the x squared minus 4's left. And in the second one I'd have that minus 80x squared. Sorry, let me be very clear about that. 80x squared. And on bottom I have that x squared minus 4 quantity to the 4th power. I can do some simplification. So this would be x squared minus 4 cubed on bottom. And on top, I'm going to do a couple steps in one. So it would be 20 times x squared, which is 20x squared. 20 times 4, which would be, or negative 4, which would be a negative 80. So I have 20x squared minus 80x squared. 20x squared minus 80x squared would be a minus 60x squared. And then again, it was a minus 80. This was all over x squared minus 4 now cubed after I've simplified. So what's the last thing that I can do there? I know I need to factor out that top anyways, so why not try factoring out the largest thing we can on top? So I'm getting, oops, sorry, let me zoom back in, f double prime of x. Looks like I can factor out what, a negative 20? And if I factor out a negative 20, I'd have a, well, negative 60 divided by negative 20 would be a 3x squared, and negative 80 divided by a negative 20 would be plus 4. And this is all over x squared minus 4 quantity cubed. So that's how they got their second derivative right there. They just say solution, here's what it is. They showed none of that work. So again, on your paper, I have to see that work. I know it takes a long time, but remember, you do have 2 hours to complete the exam. We're not done yet. We need when the second derivative is equal to 0 and when that second derivative is undefined. So the second derivative is equal to 0 when the numerator equals 0. So that'd be negative 20 times 3x squared plus 4 equals to 0. Divide both sides by negative 20 would be 3x squared plus 4 equals to 0. Subtract 4, I'd have 3x squared equals negative 4. Divide by 3, I'd have x squared equals negative 4/3. But that can't happen because a number squared can't be negative. So there's no point where the second derivative is 0. Where's the second derivative undefined? Well, the fraction's undefined when its denominator, x squared minus 4 cubed, equals 0. Cube root both sides. Cube root of 0 is 0, so that'd be x squared minus 4 equals 0. Add 4 to both sides would be x squared equals 4. Again, square root's going to give me two separate answers of a negative 2 and a positive 2. Again, these are not possible inflection points because we must remind ourselves these are not part of the domain of the function. These are vertical asymptotes, so they cannot be inflection points. But nonetheless, we do need to, when we create the number line, which I'm going to do right now, we do need to separate that number line at these x values of -2 and 2, exactly as we discussed would happen before we even started the problem in the first step. So again, we have our first interval of -infinity to -2. We have our second interval of -2 to 2, and our third interval of 2 to infinity. I know that my second derivative is undefined at each one of those x values, and I'm caring about what is the shape of my function, and at -2 and 2 I'm going to remind myself those cannot be inflection points. Those are vertical asymptotes. I need to plug these numbers into the second derivative. Again, the second derivative was -20 times 3x squared plus 4, and then all of that is over x squared minus 4 raised to the third power. I need something less than -2. How about -10? In between -2 and 2, how about 0? And bigger than 2, how about, I don't know, the number 10? Okay. I'm going to use a little bit of common sense here. 3x squared, I know that's positive, plus 4 has to be positive, times -20 has to be negative. So no matter what the number is, I know my numerator is negative. So I'm really just concerned about plugging into the denominator. -10 squared minus 4 would be a positive number, cubed would be a positive number. So that would tell me a negative over a positive is negative. So my test point was negative. Every point must be negative in that interval. Again, 0, the numerator has to be negative. 0 squared minus 4 would be negative. Cubed is negative. A negative over a negative is positive. So that entire middle interval, the second derivative must be positive. Last interval, we know the top is negative. 10 squared minus 4 is positive. Cubed is positive. A negative over a positive is negative. So that entire interval needs to be negative. So my function f of x, anytime my second derivative is negative, that function must be concave down. In the middle one, it's positive, so it must be concave up during that interval. And in the last one, it's negative, so it must be concave down in that interval. I would love to say, because it changes concavity when x equals -2 and x equals 2, that those are inflection points, but again, they cannot be inflection points because they are not defined in the original function. So what can we say? We can say there's no inflection points, or I'll just write none there. Intervals of concave up. Concave up was when the second derivative was positive. That was on the interval from -2 to 2. Concave down, that was when the second derivative was negative, so that was on the intervals -infinity to -2 and 2 to infinity. So if you go back and look at this recording, the last, 15 minutes or so of recording, 15 plus minutes, has been how they got the answers to the first part in the solution step, and all that they did in the solutions and the e-text was just wrote down each one of those answers. They showed absolutely none of the work justifying any of those answers, which is just insane. So be very, very careful. You have to show that work on the test. It's going to take you a couple pages of notes to show the work for just one of those problems. So let's take everything that we learned from steps 1, 2, and 3, or parts A, B, and C, and let's put it all onto a single graph. So what's the first thing that I notice? Well, I'm going to put some tick marks for x values here. My y values, very rarely to scale. Some things that I'm going to sketch. First thing I'm going to do is I'm going to sketch those vertical asymptotes. And I'm going to drop these all the way down because I know that I have to drop them all the way down. This is going to be x equals -2. That was my first vertical asymptote. I had another vertical asymptote at x equals 2, so I'll draw that one down. And again, I'm going to label those as vertical asymptotes, just writing VA beneath them. I also know that I had a horizontal asymptote. My horizontal asymptote was at, I'm just going to put a dash mark here, at y equals 2. I know that I had x-intercepts at the point -3, 0, and at the point 3, 0. I also know I had a y-intercept at 0, 9/2. So 9/2 is about 4.5. I don't know. I'll put it up here. There's 0, 9/2 for you. Okay. go back and look, that's my x-intercepts, that's my y-intercepts, that's my vertical asymptotes, that's my horizontal asymptotes. I believe that is everything that we knew from the first part of the problem. Let's move on to the second part of the problem, part B. What did we learn about increasing, decreasing, and maxes and mins? Well, what I learned was the 0.09 is a minimum value, so I'm just going to write min right there below it because I know I don't go below it. I know that there's no maximum values there, but also what I wanted to do was to look at that sign chart, okay? So I need to draw that sign chart directly below this. So go back to that sign chart and let's copy it at the bottom of this graph. So I've already broken it up at -2 and 2. The only other place I need to break it up was at x equals 0. And we knew at x equals 0 it was a minimum. Again, I'm looking at the first derivative. And my first derivative, it was negative on the first interval, negative on the second, positive on the third, and positive on the fourth interval. So that's all the information that I can glean from part B, step 2. Let's move on to part C, which we just completed. Again, the only numbers that I broke it up were -2 and 2. I know that there's no inflection point, so that doesn't help me, but I can copy the sign chart here. So I'm going to look at the sign of the second derivative in each one of these given intervals. So anything to the left of -2, it was negative. Between -2 and 2, the entire time it was positive. And to the right of 2, again, it was negative. Why do I care about that? Because that can tell me the shape of my function. When my second derivative is negative, I know that my function has to be concave down, the shape of a frown. First derivative negative means I have to be decreasing. So which half of a frown is decreasing? The right half of a frown is decreasing. So it has to be the right half of a frown. I look at the next one. My second derivative is positive, so that means I have to be a concave up or a smiley face. My first derivative is negative, so I have to be decreasing. So which half of a smiley face is decreasing? The left half of a smiley face is decreasing. I look at the third interval. My third interval, my second derivative is positive, meaning concave up or smiley face. My first derivative is positive, meaning increasing. So which half of a smiley face is increasing? It's the right half of a smiley face that's increasing. I look at the last interval. My second derivative is negative, meaning concave down. My first derivative is positive, so which part of a frown is increasing? The left half of a frown is increasing. So what do I do now? I put it all together on my graph. I need to go through the points. I need to approach my asymptotes, and I need to keep that shape. So for instance, I need to approach y equals 2 as I go to -infinity, but I either need to approach it from above or below. Because the shape of it, I know I have to approach below. Likewise, I need to approach that vertical asymptote x equals -2. I either need to go to infinity or -infinity, but because the shape of it, I have to approach -infinity. So it seems like the shape of this graph is going to be in the lower half, if you will, in that section, and looks something like this, going through the point -30, approaching both of the asymptotes. Likewise, let's look at this next one. I need to approach x equals -2, either infinity or -infinity. Well, because the shape, I know I need to approach infinity, and then I need to go to the point 0.9. So I'll make the left half of a smiley approaching that vertical asymptote. Same thing on the third interval. I need the right half of a smiley, so starting from the point 0.9, I need to approach that vertical asymptote, which is going to go up towards infinity. And then likewise in the fourth section here, I need to go through that point 0.30. I need to approach the horizontal asymptote y equals 2. I also need to approach the vertical asymptote x equals 2. So the way that I'm going to do that is starting low and then approach it below the horizontal asymptote, something like this right here. And from this information right here, you can look, we have sketched the exact shape of the graph, labeled all important points on this graph. We have used absolutely zero technology to get this answer. So what the book shows you and what would be equivalent of maybe a page of just answers, we have shown multiple pages of work in STEP, and I need to see that in your work on the test. I hope that helps.